Let us start our second lesson dedicated to Simulink and modeling inside the Simulink. I hope that everybody already has Simulink installed in the computer, and I will just share my screen on the part of the screen that you can also. Okay. Now you can see my Matlab and my Simulink in the next minutes, and the second part from the right, the part of the screen, it's your screen, and you can please open your Matlab. And I also hope that you have a file that I sent already, extracts from the zip file, and are located in your folder, and your Matlab is also in this folder. Okay? And now we can start. We already know with
Michael. Right now we see a lot of people on the right side. Can you somehow close it so that the screen itself will be larger?
A lot of people. No,
You have like a square, and you have like one on top of the other. So move to one on top of the other.
You know, from the left of the screen, you see now only my Matlab. Can you see something more from?
Yes, I can see your face and many of the students on the right side.
That should be set by yourself. That's not his fault.
Maybe Jeroen, it may be in your computer. You can just let me see.
Okay. So leave it. Go ahead.
Yeah, I believe it's only on your computer because. Okay. This is our screen and Matlab. Now, again, we will start with the clean Matlab. We should clear everything that it was. We should close every figures. And clean also the Matlab command window. And we will start directly from Simulink. Here you can see in the middle of the ruler of the Matlab, there is a button Simulink. If you have a long window of Matlab, you can see a nice picture of Simulink. If not, you can see only the name of Simulink. Please press this button and press the button of Simulink, and we will get the next window. On this next window, we can choose the default template of our work, of our future work. It could be blank model, it could be subsystem, but let us start from the blank model. Please press this variant. Now we have, I will make it a little bit smaller. Okay, here we have a blank editor of Simulink model. And do you remember maybe that our first meeting we already spoke about this Simulink, what it can do, that there is a input-output device graphic user interface block diagram simulator, and that the Simulink, it includes a library and a lot of tools from which we can choose to build input-output relation for our devices, for our block, for our equations. And the main subject is to know what is this ruler, what is this first diagram. Here in the ruler of Simulink editor, we have several, how to say, buttons. We have simulation, the first one from the left. We have debug, we have modeling, we have format, we have application. Let's start from the simulation. Here in this group, we have the very important for work possibilities. We can choose a new window and a new model. We can open existing model. We can save our model. We can print the model. And very important also button is library. Library browser will open our library and allow us to choose our blocks from the variety of different blocks in the simulation. Also, what is very important in this simulation, there is time for our modeling. It's stop time, how many time we will run our model. And also there are two buttons, run button and stop button. This is all is related to simulation. We will also today, we will learn about next ruler modeling. In modeling also there is important thing, model setting. Please press this model setting, and model setting will allow us to choose start time, stop time, using our type of solution of our system. It could be variable step or it could be fixed step. What is the difference? For variable is, in general, it's faster, but in some task we need to use fixed step. For example, if we need to make a modeling and to take a solution of the system for further analysis in frequency domain. For example, if we need to build a spectrum. For this type of solution, we need to use fixed step. And from the right, for the solver, we can choose a number of available solvers in Simulink. There is a Runge-Kute solution, there is Adams solution for solve differential equation. But if you don't know which one to take, you can just leave automatically selection. Now we have a button.
Okay.
Yeah.
A question. The variable step, are the step like delta x, like in numerical, like delta x, by what interval it solves?
Better to say delta t. It's not delta x or delta t. It's time variable step. Here you can see. Let me show. When you press the solver details, and if you choose automatically, there is your errors or tolerance you can choose. When you use this fixed step in this solver, you can just ask for the fixed step size. It could be automatically, or you could put here any number. For example, 1/100th of seconds. It's very also useful. I will show you why it is useful for solution of our block. It's what is very important for the how to say, modeling settings. Also very important, second line in modeling, the data import export. If we need to use our results of our simulation and to save that in Matlab or maybe in the file and use it after that, we can ask in this export and import line, we can ask to save to the workspace or to file our variables, maybe time, or maybe states of our blocks, or maybe output the solution of our equation. Also very important things. This is, I believe, enough to start with Simulink. Again, the first one, simulation itself, and the modeling and modeling settings to choose the model parameters. Now we will start from the library, because the library is our, how to say it, our box where we can choose anything for simulation. In general, this library includes basic blocks. For example, it could be blocks that commonly used blocks. There are also separators for different kind of using. For example, blocks for continuous modeling, block for discontinuous system, also nonlinear system. We also can see here the blocks, typical blocks as a sinks that allow us to see the results of our modeling. Here we can see the oscilloscope scope block. Here could be out port to extract the data to the workspace. We can also use the block directly extract the data to the workspace. We can use the block to write the result of our simulation to file. Also very, very important set of blocks, sources block. Sources is our external excitation, our signal that we will use in the modeling. Here we can say constant. We can insert any constant to our block. We can insert time. We can insert ramp function, sine function, and sine function, for example, step function, and all the others. And working with this block, first we need to know how to add any block to model. There are two ways of adding a block to the model. We can just select the block and press right button and ask add block to model Untitled, for example. Or we can drag this block to our empty model, and here we will get the block inside our model. And also there is a way to find, because we don't know all these blocks, there are hundreds of these blocks, what we can do to find block. For example, we know the name of the block. We can put in the search position of the library. We can put the name of the block, for example, scope, or maybe I would need a product. And then I press the search button, and Simulink started to find this block. And here the number of all blocks that use the name product. It could be divides, the product itself, dot product, and all variants of product. This way, searching the block is very useful to find what we need. Also, there is a very important thing, mathematical operation, math operation. Here you can see the operation that you already know from Matlab. It's called absolute value, adding some variables, and universal block that can use several math function in the library. Let me find it. Or maybe we can just use a square. I believe that there is also inside. If I take any other block here, I can choose, for example, square root value or sine square root value. And also there is a math function. Let me ask in this search math. Search. And where it is always mathematical, but I would like the general one. But let me see, maybe here, this one. When we press twice, we can find, no, it's only absolute value. Okay, we will find this. Maybe it's just used. Let me see in the commonly used. Constant we have. No, I can see this. It should be here in mathematical. Here it is, math function. You can see in math libraries, we can have a math function. Why it's good? Because it's a universal. Let's put it in our empty system. When I press twice, here in the function itself, we can choose any desirable function. It could be exponential, logarithmic, magnitude, square, power, and all you see all variants of this math function that we can choose. Okay, now we know how to find this block, and we can start to work with our first model. Let's empty it, and we will start. At the beginning, we will choose an input to our model. Input could be anyone. We just take from the source. We will take a chirp signal because it's interesting. Here it is chirp in the sources. And to add it to our block diagram, we press right button and add this block. Here we have this block already added to our model. Now, the more popular block is integral block. Let's find it. It's also a commonly used block. There is integrator. We put it here, and we can integrate our signal with this integrator. Now we can choose, just as an example, the differentiation block. Let's go to continuous and trying to find, it should be discontinuous, discrete block. Here is differential. Okay, now we have difference block. And also very useful block is just again a factor that we choose multiply or divide our signal, our solution. Also in a common block, there is example of gain, and we also press and okay. Now we have three variants of using our input signal. We can differentiate our signal. We can just multiply it by coefficient, and we can integrate it. Let's choose this coefficient. It could be, for example, 0.5. It's our gain. Let's connect. To connect different block, we also have two ways of connection. I can take my button and just connect this output from the first block to the input of the other. Another way is just select the block, press on the keyboard, press Control button, and then press another one which should be connected. And this way, but let me show how it works. I select the first one, press Control, and press the second one. This is way to connect quickly several blocks. But when the connection is already applied, we should use another connection point. We should press right button of the mouse and make a new connection to another block. Again, we should press right button and connect to the next one. Here we have three variants of our initial signal, and we can see.
Can you maybe explain it in another way how to do it, because it doesn't seem to work on my end?
What doesn't work? What exactly?
Splitting the connection.
Did you try to do it with a long press, not a short one? Keep your finger on the mouse.
Okay, I will wait for you to get all the three blocks already on this model.
Yeah, it seems to work. Thank you.
Okay.
Just so you know, you can also quickly find something instead of going to the library browser. You can click on the white space inside of here and begin typing. As long as none of the blocks are highlighted, and it'll search for the block, and you can hit enter, and it'll drop it inside of the menu.
Okay. Okay, good. Now to see the results, let's also add to our first model. We will add scope. It's also common use. We can also use it from the things. Scope also added to the model. Now we have scope. Now we can connect this signal, but now we have three variants of signal, and scope also should have 3 inputs. We can do it this way: right button on the scope and choose signals and ports. Let me maybe move it on the left to show you the result. Signals and port and number of ports. No, you cannot see, but in the number we can choose 1, 2, 3, and more. We will choose 3. Okay, here are 3 ports. We can connect directly. For example, the first one, I press again Control button, and first the output of this block and input of the scope, it is connected. The second one and also the scope, it is connected. Also this one, Control button, it is connected. This is the first variant of using. Also when we have a complicated diagram and it has many blocks, many connections, better to use very useful block named from and to. Let me show how it works. For example, we have no place for connection our scope. Let's do it this way. And again, we will return to our library and find from and to. Let's from, find, okay. And where is our from?
Sorry, you just add a display, right? You add a display? Okay.
Yeah, display. Let me, two first, let me find two. Why I cannot use it. We will find here. Okay. Go to the
Michael?
Yeah, go to.
No, someone before, he offered a better way to save time. Instead of searching, you can just double click your screen and then write from or to, and it works really good.
Yeah, also, yeah, go to. Here, this is the block. We will connect our output from the integrator to the go to block. And in the scope, we also can use the block from.
Michael, can you explain what are we doing exactly?
What we are doing, we just are trying to see different kind of blocks, how they work with the initial signal. Let's do it now just to understand what we are doing. Let me connect it, and we can just see what we are doing. In our sweeping signal, we can choose the initial frequency. For example, it could be tenths of hertz, and the time of our working could be 10 seconds, and the largest frequency at the target time could be 5 hertz. Okay, and we will see the results. Let me run our model and open the scope. Just twice press the scope, and we see the result of our simulation. We can see that there was no enough resolution to see the results of our integration, differentiation, and gain. And it means that we should decrease the step size in time domain. This is why we should go to the modeling, and we already see it in the model. We go to setup of our model, and in the model we go to the solution to the solver. Here we can choose the fixed steps and ask the more precise time of the solution arrow, the thousandths of the second. Let's apply this change and let's start again our model. And again, we will open the scope and now we can see the result. Here we can see three different signals. The first is blue color. It's our chirp signal from the low frequency to the high frequency. The red color, what do you think? It's integration or differentiation?
Differentiation.
No, it's just an integration, because you see with the frequency increasing, our envelope is decreasing. It means that if we have a sine wave, sine omega, and we make an integral, we should divide to omega, okay? And this is why the amplitude is decreasing. And differentiation, it just go with the largest amplitude, because if we differentiate, we will take the first derivative of sine omega t, we will get omega multiplied by cosine omega t, right? This is the yellow color is the differentiation. Okay, it's just this example just to show that we can work with the block, we can use it, and also interesting thing in new Matlab that we can insert some pictures here using the button from the left side. If I press this button and choose the right place, here I can see paste from my picture. Also, I can just insert any picture from here. For example, we can check, we can choose the Technion icon. Okay, as an example. Also here we can just use the annotation block. We can put here any annotation and write, for example, my first Simulink model. Also, we can choose the font size of this text.
Excuse me.
Yeah.
Where did you press to change the parameters of the signal?
Why we choose another?
Where?
You mean the time step of this?
No, I meant how did you change the parameters of the signal?
Of the signal when the initial signal, the input signal. This you mean this input,
yes.
right?
Yes,
I pressed twice this model block, and in this block I can choose the initial frequency, the target time, and the final frequency at target time.
Why is it that we use a continuous integrator but a discrete differentiator? Why not also using a discrete continuous derivative block?
Here, instead of this block.
Right. Why don't we also use the discrete integrator instead of the continuous integrator?
Differentiator. No, integrator is here. This is differentiator. No, it doesn't matter. In general, they do not recommend to use differentiation at all. It is not useful because any kind of error, initial error in our input or in our model, they will just destroy everything, because each differentiation includes a noise, will multiply all this noise in the output from this differentiation. This is why in Simulink mostly are used only integrator blocks, gain, integrator, and all other logical mathematical operation, but not differentiation practically.
How do you label the signals into the sink, so that you know when you have three different signals? Let's say you don't know what they are. How can you label them in order to see, like, input 1 is this color, input 2 is this color, input 3 is this color, into the sink?
But in the scope color,
yeah,
you just open the scope and ask in the view. You can just ask for legend, for example. Here you can see your legend. The color, the yellow color is your difference, and the blue color is your gain directly, and the integrator is the right color, okay? Also, you can just, in the view, you can choose the style of your presentation. For example, if you would like here to have a thick line, yellow line, for example, very thick, apply, okay? Here you can change it, okay?
Okay, thank you.
Yeah, it's very, very useful to use also the legend and also the colors, and also in scope it's very rich instrument. Here you can, for example, make a zoom of part of your screen of in this, how you see, you can say small details in your scope. You know, simulation is so rich, so large that you can go without any limitation inside, and learn a lot and how to use it. Very, very, very interesting. Okay. Now when we
I also have a question. I do everything as you did, but when I hit run, it doesn't do anything. But when I just click the scope, it opens the graph.
yeah,
So-
because when you press run, it cannot do so. It works. Run, it just run the simulation. It means that Matlab will all this calculation, but you cannot see anything because it works inside the Matlab, inside the simulink. Oh, I also cannot see it. Let me show. I press this button, nothing happened. I cannot see nothing.
Okay, okay.
What can be done? You can ask your scope open, be open together with your modeling and running. Let me show how you can do it. Press this twice. Press the button of the scope. Go again to the view. Go to the layout of the scope. Oh, sorry, no layout. To view, to configuration properties. And in configuration properties, you can see the variant open at simulation start. Can you see it?
Yes.
Please just check it and apply
Okay.
it. Now, even I close this scope, but when I run, I will see the results. You see?
Yes.
And also pleasant present behavior of this scope. Okay, let's continue. Before we continue, let me show how you can save your model. If you did it, you should save it. We just return again to simulation, and we press this button. This just is a standard button in the window. We just choose save as. We choose name of our model, and we can put this, for example, my underscore first. And I like not minus, but underscore, my first model, okay? Now, when we close this model and we will return to the Matlab, we can open. There are different ways of open the model. For example, first we should know the name of the, we can just ask for direct and first, my. We should know the name of our model. Then the first way is open. It just command open in the Matlab, and in the quotes the name of the my underscore first, and press the enter, and we will get our model back. Okay. The second way, we can use open system command in the Matlab. Open system, and my first. Again, we will get our model. And the third way is not only open the model, but already to start and to run and to see the result. The command is sim, the first part of Simulink. And here also we put our name of our model. my first uh, also in Simulink, we can also, there are a lot of parameters to use with command Simulink, but here the main, maybe important, is the time, the stop time. We can choose, for example, 5 seconds of our simulation and start it. This way, we not only open, we already open the results of simulation, the model and the simulation itself. Okay. Now we know how to work with different blocks, how to connect them, how to open the model, how to save the model, how to run the model, and that's all. Let's continue to do something real, just connected to the real simulation, real physical problems. Again, we clear everything, we close everything, and clean the command window. And we will start from the Simulink model that can solve the motion of the object that is falling to the ground with the error resistant. Okay, I will show the equations. Okay, here is our equations. First, we know that each object that it's falling has a constant g. This constant acceleration is denoted as g. It is a gravity of Earth or acceleration of the gravity. And the negative sides here, it means that we have chosen a coordinate system in which up is positive and down is negative. Now the differentiation equation, it includes also the inertia, the Newton law. And the third force here is the resistance of the air resistance. We know that the resistance, it depends on the velocity in square when the body is falling, and this is why the equation is just as any parameters, any factor multiplied by the velocity square of the falling body. And we will use, I would say now, the equation in the form that inertia of the falling force yeah, is equal to the gravity force and the just the force of the area that is make a resistance. They have different sign. The resistance here is a plus and the falling is minus. We should just solve what is our task. We know all these equations, and we will try to find what are the distance of falling this mass when we put it from the area. Okay, let's build this model. This model, it includes already blocks that we need. I put it there not to find them, and just let me select them and make it more color, for color black. Here are blocks that we need. Each solution of the Simulink, when we have a different derivatives, always should start from the higher derivatives. Here, the higher derivatives is the second order derivatives of the distance of our falling body, and this is acceleration of the body. We just take the integral block, and from the left it would be acceleration, and from the right it would be velocity. When we use the second integral block, the second will just use our velocity and the output of this integrator with the displacement. We can just connect them. Now, when we take this velocity, we should multiply the velocity, but before multiplying, we should just make square of the value of the velocity. Let's do it. Here, the block of the math block that will make a square. We connect our velocity to this square block, and now we should multiply this squared velocity to the factor coefficient of the area force resistance. Okay. Now we should just make a summation of all this force. We we take this summation block, and this is resistance. We already know that resistance has a plus. We just connect it with the plus, and our falling force, we just connect with the minus, and between the force and the pure acceleration should be divided by mass. We just make again, and we inside, let me choose, make more space between them, and then we connect the summation block and the mass. Now we have our modeling almost ready, and we can just to see the results with the scope. We hear the first channel we connect, we can see the displacement, and for example on the second channel of the scope we can see the velocity of our model. Now what we need two parameters to insert. The first parameter, the gravity, we know it's 9.8 meter per second square, but we need to insert mass value, and we need to insert the C as a as a force of area resistance. I already, when we use our file, we already use them. Let me check. Yes, we already have two variables, C and M. Let me see, is equal to f0.05, and the mass value is 1. Please insert in your Matlab window m is equal to 1, for example, and c is equal to 0.05, because to run the Simulink model, we need the numeric values of every variables in the model. Here we have m and c, there should be defined in the Matlab. We also, instead of define the variables in Matlab, we can define directly in the block, but I prefer to do it in Matlab. I can understand why. Let's check if it works. We start the modeling. We will go to simulation and press the run button, and we can open our scope, and here we can see that when we just leave the body falling, we can see that during 3 seconds, here 3 seconds, the displacement, the distance of our body after 3 seconds will go to 28 meters approximately. And the blue color is our velocity graph. Why I prefer to choose parameters inside Matlab, not in the, because if I need to change something in the block, I should open the block and here to press twice the value, and inside the gain of the gain block to choose to insert a different value. Instead of this, I can just put another value in the Matlab. I can just tell that C is equal, for example, much stronger resistance of the area. Let it be, for example, 1.0.1. Let us check again our block. We will run it, and we will show the scope. And here for the large resistance force, we can see that velocity is practically constant. When we have a very strong resistance, the speed of the falling is constant. The body cannot go faster than this resistance limitation. And instead of 28 meters now, we have for 3 seconds, we can fall only for 22 meters. And this is an example of how it's 22 meters. It's approximately how it's maybe 15 store department, the height of the store department. Okay, is it clear how to work, how to solve problem, and can we continue to something more complicated a little bit?
Yes.
Okay. If you wish, you can save this, but please save it with another name, not as I sent, because it's preferable to use the clean block that I sent. This way you can just repeat once again and again building of this model. Okay, I will close without saving this block. No saving. Now we will start another model. We clear everything, we close everything, and we clean. Oops. Clean the command window. And we open in Simulink. We open another model. It will be the model of mass spring damper. And we already know how to do it in Matlab, but this example will show how to modeling this mass spring damper in Simulink. Okay, but we can just run the file that I sent you. The file name is R3. Please type in Matlab command window R3 and press enter, and you will get the explanation of this model. Here is our example. Somebody told no, it's not a question. Here is our task. We should build a system, mass springs damper system, which include the mass, the spring, and the damper, and the excitation force. Our solution will be displacement of this mass.
אתה יכול בבקשה להשתיק לעשות מיוט לכולם כדי שלא נשמע את הרעשי רקע?
But if I close everybody, let me show who is speaking.
Tian, can you mute your mic?
Yeah, let me show. Okay, let's continue. We don't need working in. Here it is. Again, here we are preparing the blocks when we need to model our system, and just not to waste time, I just make them more visible, just a black color, format, and for black. Here are model. Again, as you remember, we will start from the highest derivatives. Here in our equation, the higher derivatives are also the second order derivatives of the acceleration. We will use again, we'll start from the integrator, the first integrator. The second integrator will make from the velocity displacement. These two we already can connect, and we already know that the velocity should be multiplied by the damping. We will take the damping gain here, and we connect the velocity to the gain of the damping. Here we have the force of the damping force. Now we need to make a summation of our force, the damping force and the external force all together, and also the stiffness. Now the stiffness one, it should be also a gain of the stiffness. We will connect the displacement multiplied by the elasticity, and here our stiffness force. Let's connect them together. We just connect the damping force here. Let me tell you that all these forces are going with the minus, the damping force with the minus to the acceleration, and the elasticity force also with minus. Here our elasticity will go. Okay, these two we have, and external force, again, we know already what chirp it is. We again use this chirp, and we connect this chirp to the plus, because the chirp is with the sign plus. Okay. Now what we need to just to divide with the mass value is again, and we can connect this block, just connect this one and this one. And the last thing, let us see the result of the simulation will be shown with the scope, and this scope will show us the solution, the displacement. Right button, connect the scope, and also the scope. For example, we can show the input, the excitation signal. Here I press the right button and connect the scope. Now in the scope we can see two signals, our external force, excitation, and the solution, the result of our modeling. The most important thing, just to see our sweep, our external force as a chirp. Let's press twice to the chirp, and let's see what here we can see. The chirp should be start, let's say, from 0. It could be 0. It's not so important, but the maximum could be less. It could be, for example, be let us take 30 hertz or 20 hertz, and the target, it could be 10 seconds. Let me see what we get. And well, let us run our simulation. And let's open our scope. You see, the frequency is too high. Let us, and here I can see the chirp. It's very high frequency, and this is the response of the system, very slow. It was my mistake. The frequency is very high. Let me make this maybe much less. Let's make it, for example, half of the hertz. What we have now, it's better. Let's make it less. Okay, here it's quite maybe enough to understand how it works. We will use a zoom to show the results. The color of yellow color is our excitation signal, just sign with different frequency in time. And blue color is the solution of our system. We can see that there is a resonance. We just pass through the resonance, and then we go further, and system in the higher frequency has no reply at all. It just will have zero very high frequencies. Okay, this is a variant of working with the simple first order vibration system.
I have a problem.
Sorry?
I have a problem. When I press run, it gives me an error and opens something called diagnostic viewer.
Please repeat your question loudly, please.
When I press run, it gives me an error.
Let us check. Let's check your first. Let's start from the external force, from your chirp signal. Have you the initial frequency 0, the target for 10 seconds, and the
Yes.
frequency at target, it could be less, even less. Let me take 3. Okay?
Yes, it's okay.
Apply. It's okay. Now, have you connected everything here? It is connected.
Yes, I'm pretty sure I did everything.
And
Yes.
when we press run, we can open our. We should get this example if everything. Let us check maybe your parameters M and C. Let's go now back to command window.
Maybe that's the problem.
And let's ask, please, who is, you should have here C, K, and M. C, for example, here it's 0.3, K is 1, and M is 1. Is yours the same?
I didn't get this thing, but I just did it manually right now. So,
Okay. Please run again your model.
Okay, it works.
It works. Okay, good. Now we will go to modeling the higher differential equation, third order. It's practically the same, but let us do it because it's a good practice. Again, I will close this block without saving. And again, we will start from the black. No, we can use what I sent you already prepared for this task. Let's do it. It will be, we'll go to the command window. In the command window, we clear everything and close everything. Clean the command itself. And now let's press button, our example R4. And here you can see we have the third order equation. The third, it's third order derivatives of our variable, the second order, the first order, and the variables itself. And we just start, as we know already, we should start from the highest derivative. The highest is the third order. Again, we should here, because each order requires integrator. Okay, it's now we know that it should be just very simple. We just use this integrator, and I will make them more visible and format in black color. Okay, let's do it now quickly. We use the first integrator, the second integrator, the third integrator. Okay, we can connect them by. Okay, now we can use this factor to multiply. We can multiply C from the solution. It's multiplied by C. The first derivative is multiplied by B. The second solution is multiplied by A. And we should use the summation block here. We will use it just to connect everything. Just connect A, connect from the B, and from the C. Now, also.
Why do you put the clock for?
Sorry?
Why do you put the clock in there?
Why?
Why do you use the clock? For what?
Clock is just a function. You know, there's this equation. It is written from the right-hand side. We have a function as a input to our system, and here clock is just our input. Could be T, for example, or any. We can put between the T and the input T to our summation block. We can put any mathematical function. It could be a function of T. But as a simple example, we just can use t itself as a ramp function. It will increases in time, t from 0 to maximum value. Okay, now we can make connected oscilloscope, or we can just connect output block to put the signal back to our workspace. We just use right button and connect this. Okay, now we have this signal, this system, and again, we should define all these factors. A, B, C should be defined. Let's see if we already did it. We can ask in workspace, we can command window, just write what variables we have. We have all variables. The A variables is 1, B variables is 1, and C variables is 1. Now, in the block, when we use this output to workspace, we should check if we ask the modeling block with the model setting, if we already ask to data export our results to the workspace. Yes, here you can see data import export. We already ask output to save output with the name y output to save it during simulation to the workspace. Here, save to workspace of file, and we ask to save to output. Okay, now we can run the simulation. We can say that nothing happened, but let's return to our, not here. Here we can just close to the workspace. And now when we ask who is here, now instead, in addition to our 3 factors, we have an output. Out is the structure of Matlab. We can see how it built. We can just write out and see it is built from the time, t out, and also y. And I believe if we ask what it's t out, what it is, plot, we can just plot it. Out t. Oh, t out, sorry, t out. You see, the first t out is our time. It's our time. It just increases during the time, just a ramp function. And we have also y, let me see what it is, out dot y. It has a data, and we can plot it now. Plot t, instead of out, we use y, and data, dot data. And let us see what we have. No, it's why it's not a signal. Let me check. We will ask to write to the variable name y. It should write it without limitation in time. And modeling, we ask output y output. No, it should work. Why not? And let me start again.
You didn't connect the first integrator. Is that why?
Ah, sorry. Yeah, it was my fault. Yeah, right. Let us write again. Let's go back to the workspace and plot again our data. Oh, here we have the results of our third order equation. Here we also can put it as a function of time. We already know that time is out t. We can do it this way. Out dot t psic out y. Sorry, out. Maybe it's not size. Let me check.
Shouldn't it be T out, not just T?
T out, okay. T out. Now on the axis X, we have time in seconds, not just the points of our solution. And here the our function that we solved. Okay, this way we show how to solve the third and any kind of equation. You see, it's very simple. I believe that using Simulink may be simpler than using the Matlab to solve. It depends of your choice, but no limitation to use Simulink to work with different. The same or very similar way we just can solve the nonlinear and time varying system. It's very close that we did, but let's do it quickly. We close this our block. We don't need it more. Not save. We clean our workspace and we just press the next example. We call it R5. Here our equation, initial equation that we should just make a solution for this equation. Let's do it again. Because of this equation is a second order differential equation, here we should use two integrator. We just make, where is this integrator? Here it is, oops, integral. Matlab, wow, Matlab is encountered internal problem. Don't send. Oops, it closed my Matlab. Sorry, I should open Matlab again. Okay, we will go to our example. It's example R5. Now it takes time to open Simulink for the first time. Okay, we'll need the integrator. And we need two of them. I can copy from here to make a second one. And let's do it, connect each one with an, okay. Now we can use also the scope. It will be the result of our solution. Also, we can multiply the first derivative. We can just square, make the square of this. Let's do it. And let's just press the right button and rotate, or speaking the accurately, flip the full block. Flipping block, we just repeat from, we just turn it from right to left, and we use connect right button to the block. Now we have this first derivatives in square, and now we have a sum. We should have a sum. The sum block, and just we can also press and rotate it, rotate this block counterclockwise, counter, and trying. Let's connect them. Here we can connect. Okay. And also we need to make the t, the time. Wow. Again, Matlab, what has happened? Wow. today I installed not only the recent MATLAB 28, but also 2 updates for this MATLAB. MATLAB already produced 2 updates, and that never happened before. I have a feeling that this crashing is because of the update of this MATLAB. Let me. Okay. You know what? Maybe we can do it. Maybe you can do it yourself, because it's very close that we already did. Nothing special. Only special that we have a nonlinear relation between the derivatives. Just using a square block will solve the problem.
Can you just show us how to do the t multiplied by y?
T, yeah, we just okay. Let's do it. Okay, let's do it. We use the integrator. I'm afraid that it could copy and paste. I will do it maybe slowly. Maybe this is okay. We have 2 integrators, and we already can connect them. We can insert the time block as sources. We have clock, and this clock we also can flip to go to the right direction. Okay. Now we have a multiplication. We should use a multiplication block. Here it could be this one. Also, we need to flip it. We make it rotate and flip. Okay, this is connection, our time. And here we connect our y. It's our y. It's just the output from the second integrator. Now we should make a summation. Let's find, maybe this search doesn't work well. I will use it. For commonly used block, I will have a summation. It should be here. Okay, maybe it's some block. Here it is. Again, we will flip it. And for this summation, we need the 1 and let's do it. Here we should make a square block. Let's take it from here, not from the writing inside. Square block. Square. Mat function. Okay, that we can choose here. Again, let's flip it. And choose here, instead of exponent, we should choose square. And now we will take the first derivative square, and for this summation, where's our sum? Oh, where is the sum? Okay, let's do it again. We have already set sum. Sum. Find. Let's this one. Some are going to be flipped. Okay. This is square of our first derivative. This is t multiplied by the solution, and we connected them together. And now we have the sum of them is just our second derivatives. Okay. When we now
the second expression is with the negative sign. So the summation should be with negative.
Yeah, right. And also the solution, we don't need this block here. We can do it this way. And the t should be taken with minus. The t is the first one, I believe. Let's check.
Michael, you have a new message.
Here we change the sign. Oh no, it just vice versa. The first one is plus, the minus is the second one. Okay, now we have everything correct, I believe. We need maybe the scope to connect them. Let's take the thing as a scope and connect it to the solution.
How
Okay.
did you change the sign again?
You see this summation block, when I press, it has the two symbols, plus and minus. You can choose each sign, its input connection to this block. It could be sum of 5, 7, 10 inputs. But to change the sign, you just replace plus and minus, and you will get different sign, okay?
Okay, thank you.
Now let's run this equation and open our scope results. No, again, it's something is wrong. Let me check why. Everything is connected. Maybe I know why, because it just started from 0. To see something in this equation, we need not 0 initial condition. Let's check, let's insert initial condition. Press twice integrator, and initial condition could be any, but not 0. Let's put 1 here. And we apply this. Now, again, we run this model, and we'll see the results. How beautiful is the results, right? Do you agree?
Why did you put an initial condition on the second integrator?
It doesn't matter, just not to get 0. Let's do it from the first one. Let's return 0 here, and then take something different. Let's take minus 1. On any other, doesn't matter. 5. Let's see what we get. We will start again and see the results. Yeah, still is very beautiful. Okay, now can we continue, right?
Yes.
Okay, I will show you how a gain could be not just a factor, just a simple number. It could be just more complicated. It could be a matrix. It could be a vector. It could be complex value. Okay, we will close our example. We don't need it more anymore, and we will open. The library we also don't need. Here we can, let me clear. We can just make this way clear, close all, .seek, and clean the command window, just one line. Okay, now the next example is number 6. If I'm not mistaken, it could be R6 maybe. Let us check. Yeah. Okay. What I would like to tell that here we have an example of 2 equations, second-order equation, but they are not just separated equations. There are coupling equation. What it means that x dot the time, x double dot x is a function of x, but also here is a member of y from the second equation, and vice versa. The second equation, the second derivative of y, is also the equation of y, but also it has a member of the first equation. This way, where they are connected, they are coupled. We can solve the equation as we already did in Matlab. You see, we can just use these factors and connect additional connection to this equation. But let me show another way of working with this model to work with the more complicated gain factor. Okay, Here we will open this example with the S6b, if I'm not mistaken. I prepare this equation. Right. Instead of write, let me show them together. No, this we don't need at all. How to do it? Okay. These two equations can be written in the matrix form. Can you see it in down on this our new model? We have the same equation but written as a matrix. Can you see it?
Yes.
Okay. Now let's and please take in. Now this, from my point of view, is quite complicated. We can do the same way but much more simple. Let's do it. We have now to build our system this way. Again, we need two integrators. I'm just afraid to use search inside the block because I don't know if it works. We will take integrator here and we copy it twice. Copy. I can make it just as a Control C, Control V, just copy them and connect them. It could be from the second derivative go to the first derivatives, and we need to gain. We go here and we just take gain one, and this gain we should flip to right direction. We press right button, go to rotate and flip. We flip the block, but now we should have it large because I need to put inside not just the value but a vector matrix. We need 1 and we need 2. Copy and paste. This is the second one. Now let's take the scope to see result. Okay, I forgotten to show results from the previous one, but let's do it now. Where is our scope? Okay, and summation. Okay, commonly used, some product. It should be some in common. Why I cannot see it here? Okay, let's find here, add. Okay, now the first derivatives in vector wave written form should be multiplied by a vector p and q, and we can do it very simple, just connect it to the gain as a vector. Let's connect it to the input. Inside the gain we can just write, first we should choose that there is not an element-wise multiplication but it's a matrix multiplication. This is the first. The second one, we should just write them. We should write in brackets, in square bracket, the P and Q. And okay, here we have this matrix. And in the matrix of the stiffness here, we should maybe a little bit more complicated. Should be 2 rows and two columns. Let's do it.
Could you please repeat what you did with the game, with the first game?
Yeah, here in the game, we need to make 2 things. First, at the beginning, it was just a number. Default number is 1, and default multiplication procedure is element-wise multiplication procedure. Because to allow us to work the matrix or with vector, we should choose, instead of element-wise, we should choose matrix multiplication. This is the first. The second one, here we should write exactly the column of our variables, or the row of our variables. Excuse me. Okay, and here instead of constant value, we just insert the vector. We have p as parameter, and we have here q in brackets. Can you see they are in square brackets? It's
Yes,
just a regular way of writing vector in Matlab. Now, the very similar way, we will use the force for the, here, for the, let's say, stiffness force. Here we, again, we should use the matrix multiplication, and instead of constant value, we use A and B. It's the first line, and the second row will be C and D. Okay. And apply, and okay. Now let's connect it. From the displacement, we connect to their gain, and from the velocity, we connect to the first input summation block, and we will connect to the second. We will connect our summation to the integrator, and we should now connect maybe the scope. Let's do it maybe more close, each to one, to have more place. And now we should define these parameters, this variable p, q, a, b, c, d, 6 parameters. Let's see if we have them. Again, who in Matlab? Yes, we already did it. A is -1, B is 1, C is -1, D also is -1, and P and Q. Okay, everything is ready in Matlab. Just what we need just to run. Let us run it and let us see the results. Again, again, the same problem that I show you the first. We need the initial condition, not 0, because it's a trivial solution. If you solve this equation with 0, the solution will be 0. We will need some initial condition, not 0 condition. Let's take any condition.
Is there a way to separate the initial conditions from the y and the x, so you can have a velocity or position of 1 on one of them and 0 on the other?
In this matrix way, no, they are both, because now each line consists as a vector 2 variables. If you need to make initial conditions for velocity and for displacement, you should preferable way is to work with this way of the modeling. Here you can choose a different way of each system. You can choose each initial condition, each system, because here you have 4 variants of initial condition, right? And our it's a short way. It's compact way of solving the model, but it allows you only use the solution, the initial condition for velocity, both equation, and for displacement for both equation. Let's do if it works. Let's check it. Yes, it works. Here we can have the solution.
Michael, can't we define the initial condition as a vector as well? Like we did earlier, but instead of just a constant, maybe a vector constant.
Yes, generally speaking, we can just define, but for integrator, I don't know how. Maybe here we also can make a condition as a vector. I don't know, but let's try it. I understand that initial condition should be a number. Never did it, but I am not sure that it is possible. Let's try. No difference. maybe I don't know, maybe it's also initial condition for vector connection could be also as a matrix or as a vector, maybe.
It worked for me.
Sorry?
It worked for me. I was able to get 0 initial condition for one of them and one.
Okay. I never tried it, but okay, it means that it's not only the compact way of solving this system of equation, but also it's allow us the same opportunity that the large system here this way. Okay. Now we have only 20 minutes, but let us start because very important. I think that who knows control theory should not to save. We'll work with the controller in the Simulink, and in the controller we need to use the most popular controller, PID controller. Let me explain what I mean. Here I prepare for you. Everybody already have it, has it. Everybody has it. R7 as an example. Okay, let's use it and what we have here. Okay, this is the theory of this controller. What does it mean? This controller, the name of this controller is PID, proportional integration and differentiation. What it means that the controller PID controller is a three-term controller. It's a loop mechanism that employing feedback. It is widely used in theory, in industrial, in research. And here's the block diagram of the simplest block diagram of this PID controller. How it works. First, we have a set point. Set point is just the desirable motion or desirable solution of our system, of our closed loop system. Now we will speak about closed. All our first 6 examples were just open loop system. Now we'll start it to model closed system. We have a set point desirable function, and also we have process or plant is our system, open system, which is can work but without closing, without feedback. And our system, it has a transfer function. It means that when we put inside something, we can have something output. We know the transfer function of our system. Now, when we take the output from our system, and this output with sign minus, we just make a summation with our set point, we will get error. We have a difference between the desirable function and our error. Now, what controller, PID controller, what it can do? It uses the proportional, just a factor, just multiplication factor of this error. E is an error. Can you see it? E is an error, just multiplication. The integrator part of this PID controller make an integration of this error, and it is also part of this feedback. And the third is differentiation. It makes the first derivatives of this error, and is the third, the last part of this controller. Now, let me show for a short time how it works. We can here press pause to see as example of plant. We will take a plant as our already known 1 degree of freedom spring mass system. This system, when we make excitation, when we as a step function, we will get a solution. Let me check. No, I believe that everything is okay. We just can write this equation, and here we can see the solution of this system. The solution, can we see that it's oscillated result? We know why, because the system is vibration system. It has a natural frequency, it has damping. But let's let's say that this is vibration system is a damper in our car, for example, and we need to make this damper to just using the controller to make as possible as less this oscillation, minimize the oscillation of this damper. We need to go on our road without any excitation to the car, just feel very comfortable. What can be done in this? We can just use a controller in this example. Let's do it. To make a controller, we should add the PID controller to our system. To do it, we just turn out the scope, turn out our step function, and we just select our plant. In control theory, they say plant. It's our object. Object is a plant. When we select all these blocks, all this object, we can choose the right button and ask create subsystem from selection. Okay, here we can just increase this block, and inside we can still see our system. We can press twice with the block and see it. Yes, again, this is our system, but we have input, external input and external output from this subsystem. Let's go back to our system. Now, to work with this controller, we need to connect this PID controller to our system. Let's go to the library and right here PID, and let's find it.
How do you make an
how
do you make a line out from the subsystem? I only have a line in on mine when I hit subsystem.
You should use subsystem is only part of now of your system. You should have input to your subsystem and output from subsystem.
I don't have the output though, so that's what I'm asking.
Okay. Okay, let's do it together again. I believe I can just maybe go back. Let me see. Yeah, we can go back. Okay, here our system. I know what you did. You just delete also the connection. Please delete only the scope, okay? Just the scope here and just the input excitation here, okay? This way you leave this available output and available input, just a potential input and output to your subsystem, okay? Can you do it?
Yeah, I was able to add an out block.
Okay, now we just select it again. We ask to make a block, create subsystem. Now our subsystem, we can just increase it to show you that really a subsystem inside, and we should, you know, PID, where is our PID block? Here, our PID block. Okay, we can already connect to our input, and we need just take an error. We have a summation block here. Where is our sum? We already know where is it. Sum. Here it is. It doesn't matter. It could be round. It could be. Okay. Let us use from this summation. But again, the error should be taken with the minus. We should replace the 1 plus with the minus. And okay, this is our output from our system, and we connect from the PID, and again we will use the same kind of simulation of the not good road. We can use a step function. Where is this? Our step maybe are in the sources step. I saw it here, so it should be step. Here it is, add to our block. Here is our step. Okay. Now we have the same step as we did in our oscillation system, in our amortizator, but we need to stop this oscillation. And sorry, I have forgotten scope. Now we need this scope. Scope is a sink. Okay, let's connect it. Okay. Also, we need to assign each coefficient in our PID controller. This PID controller has, as we know, 3 parameters. It has proportional parameter, integral parameters, and derivative parameters. Okay, and when I prepared for you already this parameter in the workspace. The proportional is, let me copy from here, 0.11. Let's put it in proportional instead of 1. Let's go to the integrator coefficient for the controller. It's this value, integral here, and the differential is here. Derivative is here without dot psik. Okay. Sorry, by fault. Apply. Okay, we have 3 numbers: 0.1, 0.08, 0.05. And okay. Now we are ready to run and to see if our controller is effective controller. We just run the system and we open the scope. Here the result of the force of the controller, PID controller, that the purpose of our controller was just to decrease the oscillation. We can see that we did it. We go from 0 to the steady state solution, but really without oscillation. If it is a damper in our car, it's very convenient to go to any road with this car and not feel the oscillation from the road. Okay? No answer. We have 10 minutes more. I have several. Okay, let me speak in short about what I would recommend to you.
Silica?
Yeah? Sorry?
I have a question. How do you insert the diagram first? Not the
to insert the diagram, the block.
The original, like the spring, something like that.
Because I did it when you can. Let me show you. Edit the file that I sent to you, R7. Okay. Let's see how it works. This it opened the already built systems S78. Okay, let's do it. Let's write only this first line in this file. I select the first line and I press F9. This is just a diagram, it's just a picture. It's not a real diagram, just I show you the picture, okay? The second one is this F9, and this is I try to move inside the museum. And your question, how I built it?
How did you build it, like the first one, not operations?
This it's just a picture. When I show you the first one, it's not a real diagram. It's just picture, just plot. I have it's just it's just a picture. You can copy and paste it in any editor, graphic editor.
Okay.
It's not the system itself, just picture to understand the principle of the controller. Please, you should know, because this controller is so popular. Anybody who works in Technion should know PID controller, because it's a main part of any work with the controlling and working with the system, real system. Now, okay, if we talk about popularity, I also recommend you to use, for example, in Simulink, there is very interesting model already inside your Simulink, van der Pol equation. It has only 3 letters, VDP. If you write in your command window these 3 letters, you will open this Simulink model van der Pol. It's nonlinear equation, and it also has scope. We have no time to tell about this, but please believe me, it's very useful to understand how it works, what is the nonlinearity of van der Pol, while it has a solution without any initial condition, and so on. And the 5 minutes, last 5 minutes, I believe that everybody has a notebook with the camera, with this microphone and speaker, and we can just make something maybe interesting. Let's build a Simulink model using microphone and speaker. I believe that you didn't do it. Let's do it together. We'll choose blank model. In blank model, we will choose from the library, from the sources we go, but before it's from the audio toolbox. Can you see audio toolbox? Then audio toolbox, you can see a sources. From the source, there is audio device reader. It's a microphone. Let's do it. Let's add this block to your Simulink model. Okay, here's the microphone. From the same audio block, let's take the syncs. It's our audio device writer also. Our device writer, we can connect them. Also, we can take from them, also we can take the spectrum analyzer. I believe everybody knows what it means, spectrum analyzer. We also can get the scope, the regular scope also commonly used. This also syncs and scope. Okay, 3 on there. Let's connect everybody, everyone connection to our. Now, when we write, and here we can choose the time of running our application. Let's check this 20 seconds, okay? Not 220 seconds, okay? And let's run it. Now, when I speak and when Matlab is ready, we can see my reverberation voice and also spectrum and also the time signal in the scope. Also, I can show you, you can play with this. Let me show this small block. And now, when we, for example, we can load from Matlab, also has an example of gong. It's a load gong. We can listen to this gong by using Matlab cone sound. The variable is y and the frequency, sampling frequency of s. Please listen. You can do it in your own computer because I believe it should work in your computer, which has a microphone and loudspeaker. Should use it and also listen, for example, this gong. And when we use this gong, we can also run the Simulink system to see the spectrum and to write let's do it. We will write we will execute the Simulink, and we will execute the sound gong. I execute the sound and also the sound gong. Okay, we also can do this sound maybe in more higher frequency. How to do it? We can just make a new variable y1 is equal to repeat mat file, several times. Let's repeat it. The initial file, repeat it 10 times. Dot one, it should be one column. And now let's start this Kong with a different frequency. We can sound, but now let's do it with a higher frequency, 10 times faster. No, if I can whistle, let us try. Maybe I can do it. No, I cannot. After 2 hours, I will show. Okay, but you all who knows how to whistle to the microphone can do it, and you can play and see the different frequency you will get it using Simulink. Why it is important? Because this Simulink will allow you to be connected to different hardware. In the future, we can use it to connect to different devices. We already showed in the first lecture, it could be data acquisition system, generator, it could be Arduino, it could be different system, and Simulink allows us to use different hardware devices the same way as we did with your sound card, as we did with your microphone and speaker.
What happens when you type load gong? Where does it get loaded into? And how do you know, like I don't see it in the workspace.
You cannot see, what cannot see in the workspace?
I can see there's Fs and Y in the workspace. There is something.
Oh, okay, I see.
Here the workspace. I use as example this gong just to see if it can produce the high frequency, but not so effective. Okay, more questions? No questions. Okay, thank you for 2 hours of our meeting, and be prepared for the third meeting. I believe that at the end of the third meeting, we will discuss some questions about the final project that everybody who wants to get the certificate just need to prepare, and we will explain what we will ask you to prepare. A small project will maybe take no more than 2 hours to work. Okay.
When are you going to upload the recording of the first meeting?
Because our boss asked to make some small changes in this file to put inside the good title and the end to good end, and and this editing, it takes time. I believe that maybe a day or two you will get this link in Facebook, and you will allow to use the first and the second lecture also.
Michael, I will apologize on your behalf. So basically, don't worry. At the end of the day, you will have all lectures, both in the Facebook and also in the website of the Center for Entrepreneurship and Innovation. So everything will be there. So be patient, because it takes some time to edit it. We don't want to include everything, like my talk now is useless, so we don't need it there. Let me explain you also that those of you who would like to get a certificate,